I cannot help you there. Thank you, Professor.
I'm joking, don't worry. Muchas gracias.
Listo, profesor.
Ok, iniciamos. Buen día. Mi nombre es Sergio Paniagua, soy investigador en el Laboratorio Nacional de Nanotecnología y profesor en la Universidad de Costa Rica, y seré el moderador de esta charla de la Red Latinoamericana de Física en Materia Condensada y Ciencia de los Materiales, LAFMAT. Esta es una comunidad sin fines de lucro cuyo objetivo es divulgar el progreso de vanguardia de los investigadores latinoamericanos, conectar a los investigadores latinoamericanos con investigadores líderes de todo el mundo y promover la investigación en materia condensada y ciencia de los materiales en América Latina y alrededor del mundo. I'm going to switch to English now to introduce Professor Tomás Rojas, who's going to be our speaker today. He's a professor and researcher at the University of Costa Rica on the Western Campus. Tomás studied a bachelor's in physics at University of Costa Rica, and he holds a doctorate in physics from Ohio University. And then he spent 2 years doing a postdoc at Argonne National Lab. He has done research on lithium and aluminum batteries, materials that are highly correlated in molecular materials using high performance computational techniques. So Tomás, the floor is yours.
Thank you, Sergio, and thank you everybody for the invitation. It's very, I don't know, I found it very interesting to find an organization like this. I was not aware that it exists, and I'm very happy to contribute with my little talk and anything else I can collaborate to contribute to the organization. I'm gonna share my slides now. Okay, can you see my screen?
Yes, go ahead.
I see. Yeah.
Okay.
Yeah.
Okay. Well, again, thank you, Sergio, for the introduction, and thank you everybody for coming up. This is a talk that is going to be structured in like separate projects that I have done over the years. Some of them are now getting a little bit old, and also at the end, I'll speak a little bit of what I'm working now with students. But it's organized in a way that we can see like step by step, what can we work with first principle calculations to understand design and basically work on batteries from the computational or theoretical standpoint. I titled it like that, Rational Designer Materials, Lithium and Post-Lithium Batteries via First Principles. And like I just said, we're going to start by different projects, not necessarily related between them, but they are going to be like kind of represents the different types of calculations and steps that we can do to study batteries with first principles calculations. So first, to give a very brief introduction of what a first principle calculations, just in case anybody in the audience is not familiar with. Typically, when we study material science from the computational standpoint, the ideal way of seeing it will be you have the ion, you have different electrons, and ideally we will map interactions between the ion and the electrons and interactions between the electrons. But that in reality is not the case. That, as I'm sure most of us know, is not realistic to take a material and completely model their entire electronic structure in an exact matter. It's simply not realistic, at least with the current computational systems that we have available right now. So what first principle calculations does basically is that it maps the electronic density using an average of the surroundings of the ion, and it can calculate mostly the energy of the lowest state, and it allows us to calculate many different properties, minimizing that energy. It's been widely used for many types of materials in many areas of material science. And like I said before, here what I'm going to try to explain is how we use it specifically for the points of systems related to batteries. Okay, so basically what we do, as I'm sure many are familiar, is we build the structure of what we want to calculate. We run it through a simulation using a high-performance computing facility, and that solves the system, eventually giving us properties about the electronic structure and mostly the energy of the lowest state or the ground state. There are many flavors, many branches of what first principles calculations, or what is mostly known as density functional theory. And each of them have their own pros and cons. Each of them have different accuracies, which depends on many factors. Here, what I'm going to talk is relatively not very complex systems related to the methodology, but they can escalate very quickly into a very complex system trying to model a larger system related to a battery. Another tool that we have available, I apologize for the figure in Spanish, is molecular dynamics. Molecular dynamics, what we do is related to density functional theory. There are two main ways to use molecular dynamics. There is the classical way, in which we set up the structure, in this case, typically a group of molecules. We use first guess for to assigning velocities to the atoms. We calculate acceleration and forces based on those velocities. And using Newton's law, we calculate the velocities for the next step in time. And we do that in a cycle until we are satisfied with how long the calculation has run. Classical molecular dynamics can run for scales of the nanoseconds and can easily simulate nanometers of materials. However, the drawback is the accuracy, because we're basically using Newton's laws to calculate the potential, the forces, and the velocities of the atoms. So the other way to do it will be to employ ab initio molecular dynamics, in which each step is basically use the density functional theory to calculate the potential, and that potential gives us a more accurate values of forces, accelerations, and velocities for the next step. Again, the drawback will be that it's a much complex calculation, and that makes it more difficult to run a larger system or to run the system for longer. So typically in ab initio molecular dynamics, we run it for in the scale of picoseconds. It could be between 5 and 20 is like typical values, 5 and 20 picoseconds. And the systems are typically in the scales of the tens, sometimes maybe hundreds of angstroms of size. So it's another tool. Later on, I'll speak briefly on a methodology we have been using right now to merge both of them, in using the pros of both of these methodologies. This is what a typical molecular dynamic simulation of a battery looks like. Sometimes we do just the electrolyte, sometimes we do just the cathode, sometimes we do them both combined, like in this calculation you can see here. Just a brief introduction, but to what a lithium, or in general a battery, is. Typically is formed by two electrodes, the anode and the cathode, with the electrolyte in between. Designing each of these parts and knowing the reactions between these three parts is a crucial step of understanding and predicting and calculating in general the performance of a battery. Typically, the commercial batteries right now are mostly governed by lithium ion. However, there are many types of lithium batteries that we're going to see a little bit about. And I also, at the end of the talk, I have a new project we have been working on, which is related to post-lithium, mostly multivalent batteries. Okay, as I said before, also there are several types of lithium batteries. The usual, mostly commercial batteries are lithium-ion, but there is also lithium-air with a liquid electrolyte and non-aqueous electrolyte. And there is also lithium-sulfur, which I do have one of the projects that works about lithium-sulfur. Their functioning is the same, but each of them has different challenges in the chemistry and understanding the reaction between electrolyte and electrodes that brings a little bit of challenge for each of them to improve their performance. Maybe the most important aspect of modeling a battery using first principles is understanding the solid electrolyte interface, or SEI. This is a layer that forms in the typical working of the battery, and it's a layer of compounds that typically are solvent or parts of the solvent of the electrolytes that react and break down and stick to one of the electrodes. In this picture, it's in the anode, but it can be also in the cathode. Understanding and designing the system to produce an SEI that is favorable to the dynamics of the ion in the battery is the crucial part of working and designing these components of the battery. There are species in the SEI that can help the in and out of the lithium ions, or in general, the ions of a battery. And there are species that stops it and tries to, or makes it difficult, which is part of also the life cycle of a battery. So part of the work of designing parts of the battery is to predict the formation of the SEI and predict an SEI that has favorable species for the working of the battery. And then this is mostly like what the structure of the workflow, I will say it is. We start with very prediction or calculations that are very simple. In this case, well, we have 3 compounds and we put them over a surface of lithium and we see how they react, or which one reacts with a higher energy or with a higher interaction. Then that can help us predict some of the reactions that happens between those components or solvents and the surface of the anode or the cathode. And that can help us predict what is going to form at the SEI layer in the battery. And that information we can take and then we can move it to the next stage, which is simulating an entire battery, or almost an entire battery. In this case, it's a surface or a large chunk of lithium model with a representation of the electrolyte that follows the same composition used in the experimental setup. This is the first project I wanted to talk about. It's about these compounds called partially fluorinated ethers, and they were designed to be worked on lithium sulfur batteries. So there are these 8 compounds proposed to work on different sulfur batteries. The most typical is TTE, which is here represented as compound 7. And part of the task of this project was to map their differences or see how they will compare, because the difference, the difference between these 8 compounds is their level of fluorination, meaning that it's basically the same base compound 1, but progressively it gets added more fluorines to the compound. So what we did is basically, initially we started to just trying to build the molecule, try to build the compound, and see how will they react with a surface. These are the experimental results, which gave us an indication that we could be looking at an improvement in performance if we move away from the typical compound, which is the TTE, as we increase its fluorination. So what we start doing is we select 3 of the 8 compounds, the 1, 4, and 8, which is different grades of fluorination, like the typical 4 degrees of fluorination. And we simply put them or place them over a surface and calculate the energy. So typical process in this case is to calculate the energy of the system as a whole, meaning the molecule plus the surface. Then we can calculate the energy of just the surface isolated and the energy of just the molecule isolated. And we calculate this difference between those two, and the remaining energy will be just the energy of the interaction between molecule and surface. And that energy tells us that as you increase the fluorination, you are decreasing the energy to which it attaches to the surface, which is what we call the binding energy. So it progressively shows weaker and weaker interaction. Here, the PBE represents one of the most widely used and typically used functionals to do the calculations. And PBE-D3 is one of the models or one of the many ways there are of modeling the van der Waals interaction, which is crucial in this case. We always model it with and without, or typically we model it with and without to know if there is a significant difference in the behavior after including the van der Waals interaction. Okay, so this tells us that as you increase fluorination, you decrease the level of the absorption energy. Another calculation that we can do to understand this is the pKa. The pKa is a measure of the acidity of the compound. In this case, the acidity, what it represents is a measure of the tendency of the compound to donate a proton, or in this case, the electron attached to the compound. And as you can see here, the values of the pKa, lower values of the pKa means they dissociate more easily in this case. So you can see here that also there is more or less a trend that decreases the pKa as you increase the fluorination of the compound. Later on, what we did was trying to mapping the reactions as a whole. So we took out one of the protons, or we took out a hydrogen atom from the molecule. We attach a lithium, which will be the reaction you will expect from a system like that. And we calculate the energies before and after, basically, or the changing energy after you remove the hydrogen and you attach the lithium. That will give us this energy over here. We also calculate just the energy of a single hydrogen atom as an isolated hydrogen atom. On the other side, we also calculate the molecule in a pristine way and the molecule of the lithium surface. On the other hand, we also calculate this changing here. We calculate the energy of a surface, removing one of the lithiums and replacing it with a hydrogen, and adding the energy of that isolated lithium atom that will have been removed, and subtract the surface of the lithium plus the energy of the hydrogen atom. So what this gives us is a before and after for the surface and a before and after for the molecule. Before, we take the hydrogen and replace it with the lithium, and before we go to the surface, take away one of the lithium and replace it with a hydrogen. And what those values tells us that when we combine both of those deltas of energy, it tells us that the total energy of the reaction for some of the cases, meaning for some of the hydrogens in the compound, gives us a negative value, meaning that some of them are energetically favorable. This allows us to predict not only that the reaction could happen, but if it happens, it will happen with which of the hydrogen atoms in the compound. We then combine both of the configurations after the replacing that we did, placing the molecule that we took the hydrogen and replaced it with the lithium. We place it over the surface in which we replace the lithium with the hydrogen and simulate this system as a whole. And what happens is that the lithium easily gets removed from the molecule, goes back to the surface, and not only that, but carries one of the fluorines from the molecule. And what happens also is that it pushes the hydrogen deeper into the surface, meaning that this will give us hints that there is formation of lithium fluoride over the surface of the lithium and a formation of a double bond or of a carbon-carbon double bond compound over or in the vicinity of the surface. This will give us two important conclusions. One, that there is forming of lithium fluoride on the surface of the lithium, which is a typical species that can be formed in the SEI of a battery, of a lithium sulfur battery especially. And the carbon-carbon double bond compound give us a hint that could be the initial stages of the formation of a polymer, which also could be a favorable species to be formed on the SEI. These also are some of the experimental results from XPS and infrared spectrum, and the experimental results in most cases also give us a hint that if we take a look here at the 1s orbitals of the fluorine, that there is formation of lithium fluoride, or what we have a pretty good idea that it is related to lithium fluoride on the formation of the SEI. Next stage of the presentation, or the next project I wanted to talk about, is also related to lithium sulfur batteries. But in this case, what we do is not related to these partially fluorinated ethers. In this case, we were working with the ionic liquid-based electrolyte. So in this case, what the project consisted on was that we were giving a specific ionic liquid, which is this one over here. And ionic liquids tend to be very popular in the use of in electrolytes. They have very important advantages, like they tend to have better efficiency. They tend to be very stable, so they tend to not decompose after only a few cycles of the battery. They tend to be safer for work because they have a higher temperature of degradation and minimal flammability. So in these cases of batteries, these are very desired features. So what we did in this case, what we modeled the system, but which is this is the name of the molecule, PYR14 TFSI. TFSI is this part of the molecule. And what we did was modeling it one molecule of ionic liquid, and we built a cell around it and simulated using ab initio molecular dynamics. Why only one molecule is because for the volume that we can manage in the cell is typically the concentration that you will want for this. And then we can observe how does the ionic liquid reacts with the rest of the electrolyte. And we can calculate, similar to what we did before, which was called the binding energy. In this time is called the solvation energy. So what we do is we run the cell completely, meaning the complete electrolyte, including the ionic liquid, and we also add the polysulfide. Polysulfides are these compounds that form in the lithium sulfur batteries as part of their cycling. And ideally, they will take the lithium and place it into the, from one side to the other of the cell. But it's important to know the solubility of these polysulfides in the electrolytes. And moreover, how does that solvation or how that solubility gets affected by the presence of the ionic liquid. So what we did was modeling 3 different sizes with 3 different concentrations, and we modeled the system as a whole completely, then the system without the polysulfide, and then just the polysulfide. We calculate that difference in energies, and that gives us just the energy of the solvation of the structure, meaning how strong does the polysulfide interacts with the rest of the electrolyte. And we obtain these values here. This is the concentration of ionic liquid with the DOL, which is another typical organic compound used in these electrolytes. And this is more or less what the system will look. We can see how it reacts and how it attaches to, or how it solvates the lithium ions. And what we can find is that you can tell by the solubility in these types of electrolytes, you can tell the solubility of the polysulfides by looking at the color of the solution. And what we found is that the energies we predicted, which again is related to how strong the polysulfide attaches or interacts with the rest of the electrolyte, and relates to its solubility, it related very well with the color of the solution and with the solubility of the polysulfide, meaning that increasing the DOL in this case gave a minor or a relatively smaller change in the solubility, whereas increasing the TFSI, the other component of the electrolyte, gave a much more significant change in the solubility of the polysulfide. And this not only helps them understand the solubility and a characteristic like the color, but also helps them understand or helps them decide on optimal concentration to produce the best performance and also the best solubility of the polysulfides. So these 2 projects gives us how to use first DFT alone to decide which compounds to use in a cell. The second one helps us to decide the composition of an electrolyte. But then we can take it a step higher, let's say, and we can even start to model a more complete cell or a more complete picture of the electrolyte, which is what we did in this other project. In this one, it's a completely different system. It's no longer a lithium sulfur battery, but rather just a lithium ion system. And in this, it was what the purpose or the objective of the project was to see the changes in the SEI depending on the temperature of the system or the temperature at which the battery will operate, which tends to be of very, very high importance in several systems. So what they gave us in this case was different ways that they could build the anode by different ways of growing the surfaces of the batteries, and that will produce different formation or compositions of the SEI. And we wanted to complement those with as much information as we could on the composition of the SEI, maybe a more detailed one, and what we could be predicted from the differences in the temperature. So what we started to look was the electrolyte will be composed by these 3 solvents, LiPF6, EC, and EMC. And important first step to know is if those will break down or react with the surface at different rates or any significant differences between 25 C and minus 15 C, which were the two temperatures that we were mostly interested in. What we see for the first result is that the EC does have a significant differences of about 5 picoseconds. It does produce very similar products at the end, but what we do is basically we simulate them at both temperatures and we see what comes out at the end. Both of them produce very similar products, but one of the temperatures, meaning the minus 15 C, produces it slightly different, but much faster, about 5 picoseconds faster, which is a significant time in this type of systems. On the other hand, the EMC doesn't seem to be affected by the temperature at all. It just simply comes and attaches to the surface and remain the same for both of the cases with almost identical energies. And the LiPF6 does show, again, a significance in the decomposition process, but it shows exactly or almost identical end product, which is the absorption of the phosphorus and a layer of lithium fluoride on the surface. And in this case, it's almost like a mirror effect for both of the temperatures, but one of them does it early. And again, that seems to happen at a lower temperature, which is not what you would expect. You will expect that the higher temperature helps the reactions to occur faster. Well, in this case, what we did then was modeling the more complete cell. So we modeled the electrolyte with the three components, LiPF6, EC, and EMC. We do 10 layers of lithium atoms, and we fix 2 layers in between. The reason why we always fix layers in between for most of these cases is to give an effect of the bulk in the anode surface. Right, most of these cases are not going to be, or in the case of a battery, the anode is not going to be 10 atomic layers deep. It's going to be much larger. But we cannot just infinitely produce layers of lithium in order to see the big chunk of material that is not going to react with the electrolyte. So what we do is that we fix the coordinates and we restrict the movement of those layers in order to represent, like, okay, we will expect the electrolyte to work with the first 3-4 layers of the anode, but more of there, beyond there, it will be fixed and it won't be affected. But we are mostly interested into those 3, 4, 5 layers of interaction. And what we can see here is that each of them is not easily seen, but each of them have its own differences and each of them has its own composition of the CIs. What we saw here is that we map the composition. What we do here first is calculate the per distribution function. This function, what it does is to basically tell us with what frequency a certain bond length occurs between 2 atomic species. So for instance, in this plot, we are looking, because we're mostly interested into the lithium fluoride formation. In this case, what we can see is that the lithium fluoride formation in the final stage, which is the red line, occurs a large amount at a bond length of about 2 angstroms. And then it appears at another ones with our farther away interactions between a lithium and fluorines that are slightly removed. What we did with this is calculate the differences between both of them. So what is surprising in this case was that even though at minus 15, the LiPF6 and the EC in the electrolyte tend to react faster, it doesn't necessarily translate to the formation of lithium fluoride on the surface. which occurs, as you can see here, by a higher peak at a higher degree at the 25-degree case, meaning that the composition of the SEI tends to be more governed by lithium fluoride in the 25-degree temperature, even though the decomposition rates are different and more favorable at the -15. But that's why it's so important to see at the whole picture. We cannot predict just the SEI composition looking at the decomposition of a single cell, but rather we need to model the entire environment of that decomposition to happen for it to see how is it gonna form. And then in this bar chart over here, we can see the entire picture of lithium carbon, lithium phosphorus, lithium fluoride, and lithium oxide. And that at -15 is mostly dominated by lithium carbon and slightly by lithium phosphorus, which tends to say that even though the objective of the project is to design a better electrolyte for a lower temperature, it's always gonna be tough because the whole reaction is gonna be governed by lithium carbon, which is not a favorable species to have in the SEI, and at 25 degrees is mostly gonna be, or is gonna have a higher presence of lithium fluoride, which is the most favorable species to have in an SEI. And now I'm gonna move on to the current projects we are working on. Like these three projects that I presented up until now are you saw is about lithium batteries. And there were projects that I did towards the last years of my PhD and the years I was doing a postdoc, which were kind of like an overlap, which since it was in the same group, it was a lot of the same work. But after coming back to Costa Rica, what I wanted to do is, well, obviously I wanted to still be involved in battery research. But the thing is, lithium battery research has come to a point where the competition is very, very tough. Every time you need a higher degree of complexity in the calculations, or a much larger sample, which will require much more powerful computational systems. And those are not always available at hand. Now we have been very fortunate to have plenty of computational resources, but it's still tough area to be if you don't have the most amount of resources that you have. So my solution was to move on from lithium battery, which is like the current state of battery research, because it's the batteries that we use commercially right now, into beyond lithium part of batteries, and those are the multivalent batteries, meaning batteries that instead of using lithium ions, they use aluminum, sodium, potassium as their ion to carry the charges within the cycle of the batteries. And among them, we discovered that perhaps one of the most exciting areas was designing new cathodes, and especially carbon-based cathodes, because they tend to be very stable, they tend to be relatively cheap to produce or to grow in a lab setting, and they tend to be also relatively easy to produce in mass. So it seems to indicate that eventually when these batteries come to a commercial point, they will likely be or involve some degree of cathode-based, carbon-based cathodes in their designs. So one of the cases that we started looking was these nanoparchments or nanoscrolls, which is, as it sounds, a scroll form of carbon atoms, or as you can see here in the image, is basically a graphene sheet rolled into a spiral. We started, well, before moving on, just giving a little justification of why lithium is useful to study as a battery alternative. Well, as you can see in this plot of here, it not only maps the earth crust abundance of each of the atomic species, but also volumetric capacity and gravimetric capacity. Basically give us a picture of how easy it is to obtain it and how good will be the battery in a theoretical standpoint, right? It's not easily translated the volumetric capacity to a real battery, but it theoretically gives us a whole picture. So in this plot, we can see that aluminum not only is extremely abundant, at least in the scale of comparison with the rest of these materials, but it's an extreme case if you compare it to lithium. Lithium can be very difficult to mine, and that can lead to situations or conditions that are beyond scientific research, right? It can lead to many difficult situations in which the companies or the development will want as much lithium as possible, and that will lead to obtaining it in any way possible. Well, aluminum won't have that problem because aluminum is much more abundant in the earth crust, and that translates to cheaper ways to mine it or easier ways to obtain it. Not only that, but as you can see from the blue column, is also theoretically much more capable of store charges in a set volume, which is basically what the volumetric capacity translates to. So the aluminum represents a very promising candidate to eventually replace lithium as the new ion for eventually new batteries. I think now commercially there may be one or two models used for very specific cases, but we are still a few more years to go for lithium to be replaced by any other material, and for commercially be looking at batteries made with something else than lithium. Well, now let's getting back to the carbon-based cathodes. We can see that the carbon-based cathodes are relatively easier to produce. Sometimes, like as producing graphene in a large scale, can be costly or can be difficult, but it can be a very promising material. Among them, well, they have some certain challenges. For instance, sometimes, like I mentioned for the graphene case, right? If you want to do it at a large scale, it's different to produce something so pristine and so organized on a large scale. Other case will be a carbon nanotube, which has no flexibility, right? A carbon nanotube is produced and very difficult to modify or break in the setting of working of a battery. We want something more flexible that can adapt to the conditions of the presence of ions, and we want something that is cheaper to produce. So in that sense, especially this paper, which has been our main reference experimentally, they produce carbon scrolls. They mention that is relatively or much easier to produce and synthesize than graphene or graphene-based systems. And also what is, or what they suspect, or they argument in the paper, is that is much more flexible without sacrificing stability. However, they don't have calculations to back that up. And that's where we wanted to come in and see if we can represent. First of all, we wanted to see if it really happens, or if it's really possible for a aluminum ion, in this case represented by a AlCl4 molecule, to really come in and just live inside the nanoscroll and serve as a cathode for them to be there stored, and to be easily to get them in and out the scroll. So what we did was basically that. We started building carbon nano scrolls. We started, first of all, looking at to what has been done first, and we realized that this has been studied before for systems like graphite. And in the graphite cases, they found out that the most stable way of the molecule to absorb is in this tetrahedral configuration, meaning 2 chlorines up, 2 chlorines down, and the aluminum in between. It was much more energetically favorable that if the molecule is squished to a single plane, or if 3 chlorines go to one side and 1 to the other side. So what we did was basically that. We built the carbon nanoscrolls and we started to put in molecules inside, and we started to simulate how they will look. We found 4 configurations that were really stable, meaning that for the sizes of the scrolls that we were able to test, we found 3 configurations that more or less reduced to 3, because these last 2 were very close to each other in energy and position. But we found out that the scroll adapts really well to the presence of the ion, meaning that if it is close to the mouth, it will open out and keep it in one place, meaning the molecule won't easily just leave, just based on the interaction between them. But it will stay there without easily moving out. Whereas if you move it close to the other end, it will try to move it and keep it in as close to the middle part as possible. But always, in these cases, maintaining the tetrahedral configuration of the absorption. And for this, what we do, again, is to calculate the absorption energy or the binding energy. And we again calculate the system as a whole, the nanoscroll, and the molecule, and realize that the energy's presence in those 4 configurations that were the stable points that we were able to find were negative values, meaning that they are energetically favorable, but also that they are relatively low energies in this case, meaning that this case configuration A, which is the lowest energy, is 0.21 electron volt, 0.10, 0.12, and 0.13. These are relatively low values for these types of systems, meaning not only that they are stable, energetically favorable, but also they are weak enough to be reversible, right? In this case, you don't want a system that will go take the ion and won't let it go no matter what potential difference you put up in the recharging phase. You want a system that can easily receive the molecule, but also easily let it go. And this is what these energies are suggesting. We took a look at the electronic structure of all the systems. As you can expect, absorbing the molecule will introduce new states around the Fermi level, but also this can give us ideas of the material's conductivity and a closer look at how the system will look like. And that's what we do here in a more detailed way. Here we have the pristine graphene density of states calculation of the system. And we see that upon the introduction of the system, this is in the configuration A, it moves everything. In this case, it's a bit curious. We suspect this because the deformation of the system, it opens up the mouth so much that it creates a very, very tiny gap, or a pseudo gap, you can call it, in this case. However, the system is still pretty much, it moves it towards modifying the conductivity and p-type doping of the system. Also, we can see here the other two. In these cases, where which is B and C, where the scroll keeps more of a closer shape and tries to protect more the molecule, it does clearly show more of a metallic state, and also p-type doping upon the absorption of the AlCl4. So this tells us not only that the absorption is also stable, but also taking on these systems will also produce changes in the conductivity, make it more metallic in most of the cases, which will also be good for the workings of the battery cell. Then again, this is only one molecule with the system. And what we like to do is use this as the base for building a larger picture and trying to see a larger picture of the system. Well, before that, we also take a look at the charge transfer in between them, meaning that in this case, the electron transfer from the carbon nanoscroll, which is the red, towards the AlCl4, which is the blue, meaning that what is happening is the oxidizing of the scroll. This what tells us is the flow of the electrons between the scroll and the molecule, and also where it gets stored. So here we can see the concentration around the molecule is not necessarily around the aluminum, but rather it gets very much concentrated around the chlorines. And obviously it takes away from the electronic structure or the electrons that are surrounding in the carbon nanoscrolls. So this also provides the charge flow in between them, between carbon nanoscroll and the ion, which also tends to show the high, or it relates to the high performance that the experimental paper was referring to. Then again, like I said before, what we want to do is take that and use it as the base to see what else can happen, and moreover, what can produce, what species can be produced in the SEI layer of these type of systems. What we did first was taking molecules and placing them just over the edge of the molecule. So here what we do is an AlCl3, which is the typical molecule used as the ion in the type of system. Eventually, during the processing of the battery, the AlCl3 becomes an AlCl4. An AlCl4, and also ionic liquid, which is also typically used in this type of systems. We can see that the AlCl3 is very easily broken and produce layers of the chlorine that forms in the layers. Okay, we also do modeling of the electrolyte. I'm gonna try to speed up a little bit. And moreover, we do a full simulation of the electrolyte plus a carbon nanoscroll as a cathode of the system. We do this with ab initio molecular dynamics, trying to see, again, the formation of the SEI. And what we can observe here is that we can easily see the composition. We will see easily in the other scale. Few things are very interesting from these results. We can see again the easily formation of chlorine layers there, also an aluminum there. But this point here, which is plotted in this part, but it relates to the next image, because these calculations are with periodic boundary conditions. It allows us, but I cannot go back now, but it allows us to picture the easy formation of AlCl3 to AlCl4, and the AlCl4 molecule easily going on its own without any external electromagnetic potential inside the nanoscroll. Finally, and just like in a very quick way, I'm going to mention the other part of the projects that we are working on, which is machine learning potentials in aluminum batteries. Basically, what we are doing is using a software package called DeepMD Kit, which is one of the many that are available right now. We run a simulation of AIMD for a small system. This is a very small cell, but sometimes we go up to 50 molecules, more or less. We try different compositions of the electrolyte. We pass those trajectories, forces, and energies calculated with the AIMD, and we pass them through a neural network designed by the software package DeepMD to produce a potential based on those calculations that can later be translated and used to a classical molecular dynamics, meaning that we could run systems up to 24,000 molecules, which means nanometers of scale and nanoseconds of time scale, but with an accuracy and with a very high accuracy of comparable to the AIMD systems. So right now we're working on this again for the aluminum battery systems, and we are trying to reproduce first results similar to AIMD for classical MD. We are now working on obtaining very good and very promising results, or even with very small cells, we are able to minimize the loss function or the error based on the energies and forces predicted for the systems. And as we can see here, we can map the predicted energy from the algorithm to the energy calculated by the AIMD, and same for the forces. We are able to use this software package to produce a model that can very accurately predict the forces of the interactions between one molecule and the nearby ones, and the energies that will cost. I'm also doing here a bit of a commercial. I've been very lucky to be working with several students. They are all, or most of them, belong to this computational physics club, which works out of the physics department in the University of Costa Rica. They are running several type of projects. With me will be mostly material science, but they are also working. They're very enthusiastic group of students. They have been working on several aspects of computational physics, and they are even offering services like different workshops and these type of things to the community. So I thought I'm giving them a little bit of a commercial space there at the end of the talk. Well, I mentioned most of my collaborators were mentioned on the slides, but particularly I'd like to thank Dr. Dale Ingram. He's one of my friends from the PhD. He also is a computational physics person. Sandeep Yadav, who works in Germany, he's an experimental one, and he has mostly been helping us with the carbon nanoscrolls. He even has been growing some of the samples of the carbon nanoscrolls. And to all this group of students who I'm very fortunate to have been collaborating with. Also, we are very lucky. Recently, the university purchased a new high-performance cluster, which has been helping us enormously on the calculations. And we have also a state-run one, which is Cabaret, and a research center one. So we have been very lucky in the access to computational resources. Okay, well, thank you very much. Sorry if I went over a little bit with the time, and I'll be glad to take any questions.
Thank you so much, Tomás. Very relevant research nowadays doing the efforts to decarbonize transportation among other industries. And I look forward to this aluminum-based batteries and maybe even this scroll-based batteries in the future. That'll be neat. So we're going to move to questions from panelists. And I'm going to ask, if possible, that you turn on your camera when formulating your question. So maybe let's start with Dr. Alfredo Tlahuize Flores from Universidad Autónoma de Nuevo León, Mexico. Do you have any questions, Dr. Alfredo?
Oh, good morning, everybody. Thanks for asking me to make a question for the professor. My question is regarding to the vibrational characterization of all of these systems. You showed us a lot of calculations, but maybe you forgot to mention the importance of this characterization. If you are using a molecular calculation, you need to include the vibrational, or for example, for infrared spectrum. If you are talking about these periodic calculations, you need to include maybe the phonons calculation. Can you comment where or you are using or when you are using these kind of calculations?
That's a very good question. Phonon calculations, we have used them in systems, particularly large, complex, more like solid systems, mostly to test stability. In a liquid part, I can't remember any time that we have used phonon calculations for the liquid, as we mostly want to see the reactions. So basically, the typical workflow for the liquid parts is that we let them simulate, and then we see the solvation. So we pick on the ions, and we see what is surrounded. So for liquid systems, not really. We have not used many phonon calculations, at least not at the moment. But for more complex solid systems, we even did some phonon calculations for the nanoscrolls, because we wanted to make sure we sacrifice a little bit the size of the nanoscrolls to make sure that we could combine them with the electrolyte. So to make sure that we were using with a very stable, we use obviously energetic estimations compared to other papers, but we also have some phonon calculations mostly to make sure that we are working with a stable one, which is, we know is gonna be an important point to prove, because we did have to sacrifice a bit the size.
Okay, thanks for your answer. That's all for me.
Thank you.
Thank you, Dr. Alfredo. Let's move to Professor Nguyen Thanh Tien from Canto University in Vietnam.
Yeah, nice to meet you again. First of all, I would like to thank Dr. Lewis. Allow me connect all of you for the interesting talk today. I know you simulation, you focus the material for the battery. You use many methods from the MD, electrical MD to DFT and machine learning, calculate machine learning MD. I want to know what software do you use? I know that there are many you use the software. You can show me the kinds of software you use. The first question. The second question, I want to, this is a complex the system, how you set up the supercell for the calculate DFT and the MD. Thank you.
Okay, the first question you said is about the software we use.
Yeah.
So yeah, in this case, we are not developing our own. Like we are using, I think I should have put, well, this is their main paper, but we are using a package, which is called DeepMD Kit. Is one of the many. So in this case, this area has exploded, right? It has become extremely popular. The disadvantage of this is that it's exploding in all directions and from many groups. So DeepMD Kit, I believe is a group from China, has been working on, I think they just were celebrating 8 years working on the package. So it's a well-established, well-tested, very well-developed package. It's also one of the branches. So there is also a methodology called GAP, which is from I think somebody from Argonne or from Los Alamos National Lab. There is also MACE, is another one of the branches. The disadvantage is that between them they don't talk, so you cannot use the potentials produced by one into a system from another one. Considering all the factors and mostly driven by the large community the DeepMD kit has, which gives us a forum or a number of people to talk to when we have questions, we decided to go with DeepMD kit. There is not like technical reason why to pick one over the other. They all produce very high accurate potentials, but DeepMD we went mostly because it has a very large community, and that gives us since we are not experts on this, it gives us a large number of people to talk to. And what was your second question? I'm sorry.
I want to show how to the setup the supercell, because this is a complex system. You set up supercell of a number of the atom for the control.
Yeah, so typically the software we use for building a liquid or any electrolyte is called PACMOL.
Yeah.
Is one of the many, but is the oldest and the most used one. PACMOL basically takes we estimate the concentration or the number of atoms based on the composition of experimental electrolytes, meaning in this case is 1.3 urea to AlCl3 or 1.5. Then we estimate in a volume of about 10 to 15 angstroms side, we estimate how many molecules approximately of urea and the chloroaluminate will be present in a box of that size. We gave those numbers to PACMOL, and PACMOL will take the molecules, place them in random orientations and in random places all over the cell that we want. That is the starting point. From that, we do a few tests. We verify the volume, we verify the stability, and then we run it for AIMD. And then we do a similar process in the larger cell, just with larger volume, larger number of molecules. And there is a larger process to start using the DeepMD potentials, because we have to do more stabilization of volume, temperature, energy. We basically passes through all the ensembles before we do the production runs.
Yeah, thanks.
All right, thank you very
Thank you.
much.
Yeah.
Let's see if Professor Miguel Ángel Gracia from Tecnológico de Monterrey has questions.
Yeah, thank you so much, Thomas, for the nice presentation. I am experimental, really. I don't have a strongly works in theoretical models, but I have a question respect to what is in general, what is your opinion respect to the general use of 2D materials in a new generation of batteries? Because, for example, in China, some devices start to use some metallic carbide materials based in 2D materials, and I want to know what is your opinion with respect to the capacity of this material compared with the traditional lithium or aluminum ion batteries? Thank you.
Thank you, Miguel Ángel. So in 2D, when we talk about these carbon-based ones, there are many examples of graphene-based ones, because graphene offers, well, all the advantages that we know of graphene, right? Stable, the electronic structure and all that. The disadvantage with graphene is that it's complicated to build in large scale, so that kind of takes away the motivation of working on it. But recently there has been a large amount of papers using transition metal dichalcogenides, which is like 2D materials. They tend to have a gap, And well, I'm sure you're familiar with it, and they have a large variety of properties. Like there is MOS2, which is easy to produce, have a large gap, which makes it work with certain amounts. But I think the one papers I saw, it was mostly about tungsten diselenite, if I'm not mistaken. Because again, these materials are relatively easy to produce on large scale, or one or a few monolayers, and they offer a wide variety of properties. There are also even, it was very popular for a while, I think now has decreased a little bit, is the 2D ferromagnets. I remember there are several, but I remember one with a family with bismuth. Those have been tested for certain batteries, offering like a combination of magnetic and electronic properties. But those are things are more early stages. We had a plan to work on manganese diselenite, which was also a 2D ferromagnet that could be interesting to work. But we haven't been able yet to take on the new project. But yeah, I would say 2D materials, the newer trends tend to be very focused on transition metal dichalcogenides, basically because they're a wide family with many properties.
Okay, thank you.
Thank you. Let's see if Dr. Stuart Holmes from University College London has any questions or comments.
Thomas, thank you for your excellent presentation. I don't really have many comments scientifically. It's more, so the work done at the Argon lab, is the Argon laboratory a synchrotron? Can you access experimental data on these materials that is perhaps taken in Argon? Is that why the research is done in Argon, because of the facility?
It's a big factor of it, right? The synchrotron in Argon is a big factor, and it drives most of the collaborations that involve people in Argon. In our case, we were in the chemistry department, and we didn't have direct access, or the experimental groups that we collaborated with, they did have access to it, but it was not typically used for this type of research. We did do some molecular machines research, and some other ones that the experimental group did have access to the synchrotron. But in the larger picture, yes, the presence of the synchrotron drives big chunk of the research in Argon, and is a big factor. We were a little bit to the side. We were a little bit to the
sometimes
side of it. We were working mostly with chemists. Among chemists, I was pretending to be a chemist over there. But yeah, it was not a direct work with the synchrotron people.
Well, thank you. Sorry, I don't have any scientific question. Apologies, but thank you for your presentation. Very nice. Thank you.
Thank you, Stuart.
All right, so if there's no more questions from panelists, maybe we'll move to Melvin and Jimena to see if there are questions from the social media. Jimena, are there any questions from the folks over there?
Good morning, everyone. Good morning, Professor Thomas. No, I don't have any question. And in our network, social network, we don't have any question for the professor. The people only say thank you for this incredible topic. Thank you so much.
Okay, yes, and Professor Augusto Moreira, who's here, also thanks you for the nice presentation. So I guess that maybe we'll give an opportunity for Tomás to give a farewell message to...
Yeah, no questions, thanks.
Okay, Yes, so we'll give Tomás an opportunity to give a farewell message to the audience and to the network members.
Again, thank you very much. Like I said at the beginning, I was not familiar with this organization. Thank you, Sergio, for the invitation. And I find it fascinating. This type of organization is very close to where I work. I would like to be involved, and I would like to well, also I'm very open to collaborating, to even just discussing ideas, results. I'm very open to them. Please consider me part of a member of the community. And I will very much like to be also involved in the LAFMAT organization if you will have me also. I find it extremely useful to have this kind of networking organizations. And again, thank you very much. I'll be available to any type of discussion, collaborating, or anything that I could be useful. Thank you so much.
Excellent, and thank you. Would you mind maybe stopping to share the presentation so we can see each other all with the cameras at the end to say goodbye? Yeah, thank you. Luis, want to say something?
Yeah, before.
Go ahead.
Thank you. Yeah, thank you very much for attention. I will briefly summarize this again because there are panelists which are invited today. This is the LAFMAT network, Latin American Network of Matter Condensed Physics and Material Science. And Tomás, you are welcome to be a member of this network from now on. I will send you through Sergio Paniagua all the documentation that you need to sign and contribute, and the regulations and so on. Also, we in the next month we have 2 invited speakers as well, which is Professor Nguyen Thanh Thien. He is from the Can Tho University, my friend, Can Tho University in Vietnam. Also, Professor Miguel Ángel Gracia from the Tecnológico of Monterrey in Mexico is going to give a talk also in 11 July, I think. And we are also, he's going to become a member as well later on of the LAFMAT network. And we are going to present some application for funding later on as well in order to have internal mobility between Latin American countries and laboratories and so on. Well, maybe some of you don't know Professor Stuart Holmes, who is today here. He from the University College London, and Professor Clauise, who is the University of New Orleans. There are other members. Augusto, are you there? Augusto, ¿estás? Augusto. Augusto Moreira is from the University of Pernambuco in Brazil, and many other members were briefly connected, but they left because it's very early morning there in Latin America. So, for example, Augusto is from Brazil. In Brazil is 11:30 a.m., but in Mexico is 7:30, 8:30 a.m. So that is why sometimes in Vietnam this moment is nearly 10 p.m. for example.
Yeah.
So, well, that's thank you very much to be attended. And every Saturday you have the link, and every Saturday you can join whenever you want. And Tomás, we are going to connect you later on through the documentation that you need to sign. Okay, thank you very much. Sergio, do you allow me to close this meeting today? Ok, muchas gracias. Miguel García, también te voy a estar comunicando luego a través de email. Ok, thank you very much. Nos vemos la otra semana. Thank you. Cheers.
Ciao. Thank you. Thank you.
Bye.